Hello, hello, hello. Is anyone there? Hello? Hi. Hello. Someone say hi to me in the chat. Is anyone there? Am I by myself? No, I couldn't possibly be. Hello? Hi. I feel so lonely. Oh no. Oh no. Come on, so I can see you. I can't see you. That would be really weird. Hi. Okay, well, Mina's here. Thank you, Mina, for starting off the chat right, as one of our lovely moderators for today's lesson. Do we have anyone else that's gonna say hi? It's just gonna be me and Mina and I. Shout out to you, Mina. Thank you so much. Well, I hope that you'll hopefully maybe help us with answering some of these questions. If no one else wants to talk to me, I'm not scary, I promise. Okay. Maybe you'll want to um speak to me more once you know who I am. So let me do a quick introduction for those of you that are here. Yay, Yashi. Hi. Hi, Yashi. Are you like Yashi from my classes, Yashi? Hi. Yeah, hi. Every yay. Oh my gosh. Excellent. Glad to see you here. Yay. Okay, let's get started for our year 7 free stream. Okay, why not? Hi, Nikki Simone. Hola, hola. Bonjour, comment ça va? Let's do a quick intro for our lesson. Thank you, every. I appreciate you. So hi, that's me. Hang on. That's me. I am LaJoy Tucker. I sound like James Bond there. LaJoy Tucker. I teach chemistry here at my Ed Space. I went to Oxford University and I studied chemistry there, and I've been teaching ever since. I've been teaching for, I know it says over 10 years. This is actually year number 12 of me teaching, which is very exciting. So stick with me because I've got you when it comes to chemistry. So for year 7, hi Lara. For year 7 science, you do all three sciences. So you do some biology, you do some chemistry, and you do some physics. But we'll be doing a lesson talking about chemistry this afternoon. Do we have any questions before we get started? I am also going to show you, because we don't gatekeep around here, right? If you know other people, right, from your class, from your family, from your friends, whoever, that you feel like could benefit from an extra science lesson for year 7, or if they're not in year 7, maybe they're in year 8, maybe they're in year 6, and you feel like, hey, yeah, come along, let's do some science, then you could just copy and paste the link for this stream and send it along to them and just go, hi, come join this lesson with me, and then we can chat about chemistry. We can talk about particles all together. Oh, how old am I? Oh, I'm sweating. Am I sweating because I'm scared? I'm joking. How old do you think I am? Ooh, I'm joking. I am 33, but it's my birthday next week, so I'll be 34. And feel free to send gifts. Thanks. Okay, have you shared this link? Lovely. Hi, Lara. Have you shared this link with anyone? Anyone that you feel, ooh, come and do some chemistry with me this afternoon? Anyone shared it? I'm going to take that as a yes. I'm going to take that as a yes. Yeah. Okay. My birthday is not this Saturday. No, oh my gosh, when is my birthday? Not this Sunday, but the Sunday after, the 14th. Okay. Those of you that are here, well, are you ready to get started with some chemistry? Give me a yes, give me some exclamation marks, give me some yays in the chat if you're ready for us to start some chemistry now. Yay, we're ready. That's me pretending to be you. Are we ready? Thank you. Hi, Joy. Oh my gosh, your name is like mine. Hi, Joy. Welcome. Okay, let's get started. My last name, let's go back here. So my name is LaJoy Tucker. So first name LaJoy and then last name Tucker. You can call me LaJoy though. You don't have to call me Miss or Miss Tucker if you want to. If that makes you feel more comfortable, then by all means. But you can just call me LaJoy. Okay, or you can just call me hi, or excuse me. Thank you, Every. Okay, let's get started. So this lesson is all about particle theory, which essentially explains how matter behaves. Now, when we're talking about matter, we're talking about just like stuff, right? Everything is made up of matter, which means everything is made of stuff. Now, the states of matter we might be familiar with already. Three main states of matter: solids, liquids, and gases. So let's start off. Can you tell me from these objects over here on the right-hand side, which of these are solids? Let's start with that. Which of these are solids? I'm going to put the first one in. I'm going to say the Earth. Any others of these you would put in our solids column? Have a go, have a go. Who's going to be brave? Give me some suggestions. Which of these are solids? Thank you, Yashi. Iron. What else do we have? And think about how you know it's a solid. I'm going to ask you that later on. Thank you, Every. Steel. Let's cross them off as we go. Rubber. Thank you, Lara. Hi, Melvin. Okay, hi, Melvin. Welcome. Hi. Any others from here? I can see, I think at least two more. I think at least two more. Glass, although some people argue that glass is actually a liquid, but we won't go there today. Any others? Okay, got you. Thank you, Melvin. I'll try to remember, but if I forget, and I call you Joy, I apologize. Please do remind me, but I'll try to remember Melvin. Okay, Lara, ooh, maybe try refreshing. Rubber, we've got already. Honey, so Tawana, you make a good point. Honey, I think we can put over maybe two columns because it depends on what type of honey maybe you've got, right? Some honey, like this one, we can looks more like a liquid, whereas if you have set honey, then that's more like a solid. So I would put that possibly in both. And same with wax, Every. Wax, it again depends on what type of wax you've got. Okay, here, to be fair, it is solid, so maybe it belongs more over on this side. Now, let's go to liquid. Oh, and flour. Does anyone say flour? Let's go to liquid. Oh, I see, Lara. Okay, fair enough. Fair enough. For liquid, which ones of these can we sort into our liquid column? Also, just from the ones that are on the screen. So honeycomb would be a solid, but just from the ones that are here. Thank you, Every. So we've got juice. We've got possibly honey, could go in both. We've got, does anyone say water? Thank you, Yashi in capitals. Love to see the enthusiasm. And wax we put in both. I think that's probably about it. And finally, let's go to gases. Which ones of these are gases? Thank you. Hi, Gomina. Ooh, Every, I suppose it depends what type of sugar you've got, but I think we can say really sugar from the sugar that's on the screen. That's definitely a solid. Let's go for gases from the options that are on the screen. I agree, Laura. Steam. So steam, Tawana, I agree. But let's see just from ones that are up here as well. Any suggestions from the ones on the board? Oxygen. Thank you, Melvin. Methane. Hi, Esther. Welcome. Really, it's the ones that are left over, right? Nitrogen. And if we take oxygen and nitrogen and mix those together with some other gases, we actually get air, right? Air is a mixture of gases. Now, you'll talk more about mixtures on the main course, poison gas. To be fair, Melvin, there are lots of different types of poison gases. But now, we sorted those into the columns just based on kind of what we understand already about solids, liquids, or gases. But how did we decide? What sorts of things were you thinking about when you were going, oh, yeah, that one's a solid, or that one's a liquid, or that one's a gas? How did you figure it out? What were you thinking about? Do you just know it automatically? And if so, how? How do you know? How do you know? How do we know what's a solid, what's a liquid, and what's a gas? What did we think about? The structure. Ooh, Yashi, I like that. So often we think about the structure and we're thinking about how the materials behave or we're absolutely about to start talking about that. So we start to think rather about their behavior, or the other word or the other term that we're going to use for that is the properties, right? How a material behaves can help us decide whether it belongs whether it's a solid, whether it's a liquid, whether it's a gas. So let's summarize some of the properties of these states. So the main properties that we're going to consider is whether or not it keeps its shape, whether or not it keeps its volume, whether or not it's able to flow, and whether or not it's able to be squashed. And I'm going to be more specific here, how able it is to be squashed easily. Okay. To be fair, Melvin, you're not wrong. So let's start with solid. Do solids, let's take an example. Let's take my phone because it's right here. Does a solid keep its shape? Does a solid keep its shape? So whether I put it on the table or I put it outside or I put it on the floor, is it going to still have the same shape? Thank you, Susan. Welcome. Yes, indeed, it will. Wonderful, does a solid keep its volume? When we say something keeps its volume, does anyone know what we mean by that? Something keeping its volume? Hmm. Any suggestions? Think about it like maths. Have you seen volume in maths before? Hmm. When we think about volume, we think about how much space it's taking up. Okay, so if I say, does it keep its volume? That means, is it still taking up the same amount of space, even if it's in a different environment, essentially? Okay, and a solid absolutely will take up the same amount of space. My phone, whether I put my phone in a cardboard box, whether I put my phone on a plate, whether I put my phone in a cup, my phone is going to take up the same amount of space. That's my phone. I'm a fantastic artist, in case you couldn't tell already. Let's go to the next one. Are solids able to flow? Are solids able to flow? Yes, no, maybe so. What are we thinking? I agree with Susan. No. Lovely. And finally, are solids able to be compressed or squashed easily? Capital no. Thank you. No exclamation mark. No, they are not. Wonderful. Lovely. Let's go to liquid. This one might be a little bit trickier, but let's see, because we're doing so well so far. Let's see if we can keep these good vibes going, right? Do liquids keep their shape? Do liquids keep their shape? No, I agree with Susan. Lovely. And Yashi and Lara and Melvin and Esther and every no multiple exclamation marks. Depending on where we're putting a liquid, that is going to take the shape of its container. Lovely. Now, does a liquid keep its volume? Does it take up the same amount of space, even if we place it in different containers? Should we do a poll for this one? I think let's do a quick poll. Does a liquid keep its volume? Yes or no? Let me know in the poll. What do you reckon? Hopefully you can see it. Hopefully it popped up for you on your chat. Okay. We've got a couple of votes. I'm going to give you, let's say, 5 more seconds to get your votes in. In 4, One. Okay. 87% of you are saying yes, and I agree. A liquid keeps its volume, okay? Even if, double check the volume on your device as well, Lara, unless are there volume issues across the board? Now, when we put our liquid into different containers, it might take a different shape, but ultimately, if we were going to calculate the volume, it would be the same total volume, the same total space that is being occupied. Okay, lovely. Thank you, Lara. Next, are liquids able to flow? That's me flowing. Are liquids able to flow? What do we reckon? Think about water. Thank you. Hi, Parminda. Welcome. Yes, indeed. And finally, and we might do another poll for this one. Can we squash? Can we squash or compress a liquid? Mm, in the poll, please. And if you're not sure, maybe put some liquid in your hand and try and squash it. Not over your computer because you might destroy your device. Don't do that. Can you easily squash a liquid? Oh, hi, Preetsima. Welcome. Hi. I'm going to give you another 5 seconds to get your votes into the poll. We're quite split here. We're close to 50-50, actually. Who's going to tip us over the edge? Any more votes coming in? Ooh, in five, in four, three, two, and one. This is always a bit of a tricky one. Can we squash a liquid? Well, if you put some liquid, some water in your hand, and then you try and squash it, what happens? What happens? Does the water then take up less space and get closer together? No, it will just fall out of your hand. Okay, we cannot easily compress or squash liquids. And we'll be able to explain that a little bit better when we start to look at particle arrangement. Okay, they cannot be easily squashed. Okay, when we start to look at the particles, that's going to make so much more sense if it's not quite clicking already. Finally, let's go to gases. Do gases keep their shape? Yes, no, maybe so. Yes, no, maybe so. And don't forget to share this link with anyone that you think might want to do some extra science this afternoon. No, lovely. Depending on where we put a gas, it's going to, again, take a different shape. Does a gas keep its volume? Does it always take up the same amount of space? Lara, absolutely not. Gases will spread out to fill whatever container they're in. So if we put our gas, let me change color again, just because I feel fancy. If we've got the same amount of gas, if we put it in this small container, it's going to fill the whole space. If we put it in a bigger container, it's going to take up that whole space. If we put it in an even bigger container, sorry, it's going to fill that whole space. So it's going to spread to fill its entire container. Okay, it's not going to keep its volume. It's going to take up whatever space it's put in. Wonderful. Are gases able to flow? I think Melvin kind of answered this one for us earlier, talking about air. Can gases flow? Kind of, yes, they can. Right? Gases, oh, I was almost about to give a spoiler. Oh, no spoilers. Yes, gas. Oh, I'm going to give a spoiler again. I'm not going to say any more because I want to save that. And finally, can we squash or compress a gas? Yes, thank you. Capital yes from Yashi, and I would have to agree. Again, similar reason for volume. If we've got our gas in a really large container, if we make that a smaller container, then the gas is just going to get closer and closer and closer together. Now, the compressed part, that might be a little bit tricky to get your head around, but will make a lot more sense once we start to think about what makes a substance a solid, a liquid, or a gas. And what makes a substance that particular state is all about the arrangement of something called, but what was the title of the lesson? Something called particles. Okay. Now, particle theory says that every single thing, all matter, all stuff, is made up of particles. And we can think of them like little, like balls, like spheres. Okay. Are we happy with that so far? So we can think of particles as being like spheres, 3D balls, and how these particles are arranged will determine the properties, okay, how that substance behaves. Now, can you tell me in the chat who's heard of particles and has seen how particles are arranged in different states before and can kind of maybe help us out? Because particles are arranged differently in solids versus liquids versus gases. Okay, have we seen it before? So you're going to help me out. I'm putting some faith in you right now. So when it comes to a solid, how are the particles arranged? Oh, where's my pen gone? Hang on a second. Okay. Oh, spoiler. How are the particles arranged? How are going to put our circles, our spheres? Oh, we've gone quiet. Are we still there? Hello? Oh, thank you, Lara. So you started from gas, so I'm going to come back to you there. And with liquid, for solids, absolutely, the particles stay in place. So we can put our particles in layers. Oh, I've run out of space. There we go. Like this. Wonderful. Lovely. Lovely Preet Simar as well. Now for liquids, thank you. One clump and they stay together. When it comes to liquids, as Lara said as well, they don't separate too much. The particles are still quite close together, but they're not quite so regular. Okay, instead, they're a bit more random and they can move around each other. Okay, I agree with Mina. Even if you're not sure, still give your suggestions. Lovely. Not very even, not very regular, moving over each other. And finally, in gases, the particles are really far apart. Okay. Now, once we consider the arrangement of these particles, that helps us to explain how they behave. Okay, lovely. And before we start to use some of these key words, I think maybe let's have a look at some particles. Does anyone want to look at some particles? Let's look at some. Okay. Now, I think this link is in your workbook as well, right? There is a workbook link down in the description of this video if you want to follow along and if you want to maybe have a go at this simulation yourself later on. Okay, so at the moment, this state is which state? Is it solid? Is this liquid? Or is this gas? What we can see here on the screen. Is this solid, liquid, or gas? What do you think? Based on what we just saw. Any suggestions? Thank you, Susan. Lovely, solid, right? And as we can see, like we saw on the previous slide, the particles are in nice, neat, regular layers, okay? But also notice the particles, they're not completely still. What are the particles doing? What are the particles doing? Feel free to do it along with the particles too. What are the particles doing? Thank you, Lara. The particles are vibrating. So they're not moving around, right? They can't move around freely, but they're on the spot, fixed, and they are vibrating. So they've still got some energy while they're vibrating on the spot. Now, if we start to heat this up and give the particles more energy, what's going to happen to these particles? Well, if they've got more energy, they're going to move even more and they're going to get further away from each other. And what state are we going to get? Oh. Come on. Let's heat it up a bit. Come on. Lovely. Now they're going to move apart slightly, start to move over each other, further away, more energy. And now we have got a liquid. Wonderful. Now, if we give them even more energy, what's going to happen to these particles? Well, they're going to get further away and they're going to move even faster. And what state are we going to end up with? Some of those particles are going crazy right now. Okay, okay, chill. Actually, no, don't chill. Lovely, well done. Now we've got a gas. Okay, so what can we see? We go from solid to liquid to gas. The particles have got more and more and more energy, and the particles are further away from each other. Wonderful. Okay, let's put some of these words into, some of these keywords into action. Lovely, we're going to use some more of those later. So let me get rid of this here. So what keywords then can we use to describe the arrangement and the behavior of the particles in our three states? So for solid, what keywords can we use in this box? And there are some keywords up there, so you can use those to help you out as well. No worries. I know you're here and I know you're locked in, so well done. What do we have? What keywords can we use? Hi, Shiv Kumar. Yes, indeed. Which words can we use from over on the side to describe the arrangement and behavior of particles in a solid? Thank you, Lara. We can say fixed. The particles are in fixed positions. What else can we say? What else can we say? They are stuck together, right? So we can say they are very close / stuck. Again, let's stick currently to the words that are on the screen, okay? In terms of how they are arranged, what can we say about that arrangement? It's very, thank you, Every, it's very ordered, aka, we heard this word earlier, it's very regular, right? It's nice, neat layers, one on top of the other, nice, ordered, layered particles. Any other keywords that we can use from over there, over there, over there? I could see one more that we can use. How do solid particles move? What kind of movement do they exhibit? Thank you, Melvin. They vibrate. So instead of moving around, they're in fixed positions, but they are vibrating in those fixed positions. Wonderful. Let's go to our particles in a liquid. And remember, you can use these keywords more than once. So if we think about these particle arrangement, are they close or are they far? Close together or far apart? What do we reckon? Close together or far apart? Thank you. Snipe bite. What a name. Hi. Close together. Still quite close together. Can they move or are they stuck? Can they move or are they stuck? Think back to the simulation or even click back into the simulation if needed. Thank you. They move. And Susan, fantastic keyword that wasn't even on the screen, but I'm definitely going to add that in. Instead of the arrangement being ordered or regular, the arrangement is very random. And that's because their movement is random as well. Wonderful. Now, before we go to gases, okay, can we start to see, based on the particle arrangement, why we can't squash or compress solids or liquids? Why do you think we can't squash them based on their particle arrangement? Why can't we squash them easily or compress them easily? Is it starting to click? It's not because they'll just move. In order to squash something, if we try and squash these particles closer together, is that possible? Look at the solid. Is it possible to squash these particles closer together? Is it? not about randomness. Thank you, Lara. They're already squished, right? The particles are already really close together. There is basically no space or very little space between the particles. So how can you squash something if there's no space to squash them into, right? That's why it's very difficult to compress solids and liquids because there isn't enough space between particles to actually squash them closer to each other. Does that make sense? Give me a yes, give me a no, give me a maybe so. Lovely. Thank you. Great. We're going to come. Lovely. Okay. Let's now move to our final state, gas. What keywords can we use? And again, we can use some of these keywords again, words that we've used before. Lovely. Particles are far apart. Thank you, Snipe By. They move. And again, they move randomly, as we saw before. Wonderful. Excellent. Now, also in that simulation, we saw that we can change states from one to another to another. Okay, what did we do to turn a substance from a solid to a liquid to a gas? You're absolutely right, Melvin. You're absolutely right. We would need a lot of pressure to do that. What did we need to turn that substance from a solid to a liquid to a gas? Lovely, Lara, to heat it up. Because what were we giving the particles as we were heating it up? What were we giving the particles? Oh gosh, I can't draw straight lines. Let's pretend that this is really neat. Thank you. We're giving them more energy. More and more energy. And there are names that we give to these changes of state. So let's see if we know them. Let's see if we know them. To go from a solid to a liquid, what is that state change called? When we heat up a solid and it changes to a liquid. Ooh, Melvin, that's plasma. When we heat up a solid and it turns to a liquid, thank you, Evie, we call that melting. If you're ever not sure, my trick for remembering the states of matter and the changes of state is to just think about water. Okay, so if we think about solid water as ice, we think of liquid water as water, and we think of gas water as water vapor or steam, then we can clearly start to think about what these state changes are called. So solid to liquid, we call that melting. What about, hi, Zimbabwe Daily Online TV, hello. What about going from a liquid to a gas? What do we call that change? Every, you're on it. Wonderful, boiling. Excellent. You might also see evaporation. Evaporation is when a few particles turn from a liquid to a gas. Boiling is when all the liquid particles are now separate and we've now got a gas. Okay, lovely. I'll put slash evaporating, but you'll look more into the difference between those two keywords a bit later on in your studies, maybe up in year 9. Okay. Now, that's heating. When we heat up a substance, we can go from a solid to a liquid to a gas. Now, if we cool it down, we can go back the other way. So let's start with gas to liquid. How do we go from water vapor to liquid water? Think about on a window. What do we get? Water vapor, thank you, condensation or condensing. And then finally, Lara, you've got that last one, from a liquid back to a solid. So from water to ice, then that would be freezing. Oops, can I spell? Usually. Okay. Are any of those keywords new? Do you have any questions about these state changes? So if we heat, we can go from a solid to a liquid to a gas. We can give those particles more energy, okay? And we can make those particles move further apart. If we now cool the particles down, then the particles are going to have less energy. They're going to get closer together and they're going to move more slowly. Condensing snipebite is from a gas to a liquid, right? Our state change from a gas to a liquid is called condensing or condensation. What about oobleck? Oobleck is a bit of a weirdo, and by all means, make some oobleck. Great question, Lara. Oobleck is classified as a non-Newtonian fluid, right? Because it doesn't really follow the rules. Sometimes it acts like a liquid and sometimes it acts like a solid, depending on what you do to it. Okay, and you can make it really easily at home using cornstarch or corn flour and water. So I would strongly recommend make sure you've got permission first, right? Because it's quite messy, even though it's very safe, but it's still quite messy. So make sure that you have permission. Snipebite, great question. Heat energy. Heat energy. If we give the particles more heat energy, then that turns into kinetic energy, meaning that the particles can move some more. Great question. It does sometimes feel like a liquid, but then if you try and like punch it or like smush it, then it feels like a solid. Or if you like squeeze it, it kind of turns into a solid. Okay, let's start to test our knowledge because I think we've learned quite a bit today. Let's summarize. As we go from a solid to a liquid to a gas, the particles have more what? From a solid to a liquid to a gas, the particles have more. Ooh, there is more space between the particles. Lovely. Ooh, I'm gonna add that. You guys are too smart for me. Let's add that. They have more space between them. And what else do the particles have more of? Thank you. And they have more energy. Lovely snipe bite. Shiv Kumar, every wonderful. They have more space between them and they have more energy. Right? Again, think about these particles as a solid, just chilling, vibrating, liquid moving over each other, and then gas all over the place. Okay? Now, one step further. Between these particles, holding these particles together are like forces, right? Like think about them like they are like they're almost holding hands. Okay? Now in a solid, those forces, do you think they're the strongest or do you think they're the weakest between solid particles that are stuck close together? Do you think there are really strong forces holding them together or really weak forces holding them together? Lovely. Very, very strong forces, the strongest forces holding them together, right? Think of them like really like holding hands. But then as they change state and then go to a liquid, what happens to those forces between the particles? These are the forces, my fingers, between them. Lovely. They get weaker, slightly weaker forces between particles. And then when we go all the way over to gases, what do you think happens to the forces between those particles? Even weaker. Lovely. So, to summarize, as we go from solid to liquid to gas, the forces between particles become, what word then goes in this gap? As we go from solid to liquid to gas, the forces between particles become, thank you, Susan, become weaker. Wonderful. Particles have more energy. Particles have more space between them, and the forces holding those particles together get weaker. Wonderful. I'm not going to give you more information. I want to test or check. Let's not say test. Let's check how well we can now recall and apply and understand and bring back that knowledge. I agree with Mina, great stuff. So let's start with a quick true or false. In the chat, I just want you to give me a T for true or an F for false. Okay? T for two, F for false. Hang on, Snipebite. Let me see your question. The particles in a solid force. So the force holding them together, they're like bonds, right? Have you heard of like chemical bonds? That's what's kind of holding those particles together. Okay. Kinetic energy means movement energy. Okay. You're very welcome. Solids can flow like liquids. Okay, false. Great. Let me get my highlighter out. I agree. False. How do solid particles move? Actually, no, let me not spoil it. Let's go to question number 2. Particles in a solid are closely packed together and vibrate in place. True or false? I'm seeing lots of T's for true. Oh my gosh. Wow. Interesting. Don't know how I feel about that. I don't know how I feel about that. That's okay. I feel good about the answer, less good about that color, but it's okay. Well, it's okay. Right. Question number 3. Forces between particles in a gas are stronger than forces between particles in a liquid. Let's see, let's see. Hi, Maiwa. Are you Maiwa from the main course, Maiwa? Hi. If not, then welcome. Well, welcome either way. I'm seeing all false, and I agree. Forces between particles in a gas we saw are actually the weakest, right? Solid. Hi, Maiwa. Yay. For a gas, sorry, for a solid, really strong, like bonds holding them together. Liquid, weaker, and then gases, much weaker than that. Lovely. Okay. F. So 4 is what I meant to say. No spoilers. 4. Condensation is the change of state from a gas to a solid. Myra, it took me a minute. Do you know why? It's out of context. I was like, you're not year 7, but thank you for joining us anyway. Hi. False. I agree. What should it say? Condensation is the change of state from what to what? What should it say? What should it say? From a gas to a, thank you, Tawana. It should say from a gas to a liquid. Great. And finally, the temperature at which a liquid turns into a gas is called the boiling point. True or false? Hi, Samvish. Wait, you got it. Ooh, I want to see a couple more answers first before I confirm or deny. Lovely. True. Liquid to gas is boiling, and the temperature that a liquid turns into a gas is called the boiling point. So for example, if we wanted the boiling point for water, the temperature that water changes to a gas, does anyone know what that temperature is? Any suggestions? Anyone? Have a guess. Even if you're not 100% sure, have a guess, have a guess. What temperature does water turn into a gas? Lovely. Okay, no guessing needed. 100 degrees, absolutely. But different substances will have different boiling points. But water's boiling point is 100 degrees C. Snipe bite, that is a great question. And talking about elements and compounds, that is the sort of topic that you'll see as part of the main course, right? When you go through your topics in detail. But an element essentially means it's just one type of particle. Oh, that's not true. That's not true. One type of atom. Okay, which will go into more detail. Okay. Should we do a couple more practice questions? Esther, what's up? Esther, what's going on? Are you okay? Let's do a few more. What are the 3 traditional states of matter? Ooh, Yes, so snipe bite. In your periodic table, all of those are your different elements because they're all different types of atoms. Okay? Okay, give me a letter. I'm seeing lots of A's and I agree. Lovely. Let's go next. Number 2. Which state of matter has a definite shape and volume? For this one, I'm going to do a poll. I'm going to do a poll for this one, so bear with me. Think about your answer, and then I want your answer in the poll. Wait, no spoilers, no spoilers, no spoilers. Wait, wait, wait. Ah. Which state of matter has a definite shape and volume? In the poll, please. Can you hear me? Oh, wait, okay. I was whispering so quietly that the mic couldn't even pick it up. That's crazy. Okay. Okay. I'm going to give you 5 more seconds. If you haven't voted yet, have a go. Even if it's wrong, I'll never know. I'll never know. I agree, Lara. I'm going to end the poll in 5, in 4, 3. That's so true, Sniper. We're doing really well. 92% of you said, oh, spoiler, said C, solid, and I would have to agree. Now, a couple of you said liquid, and there we need to be careful because this question is which state of matter has a definite shape and a definite volume, or a fixed shape and a fixed volume. Now, liquids have a fixed volume, but do liquids have a fixed shape? Do liquids have a fixed shape? No. Right? Liquids will take the shape of their container, right? Okay, next one. I'm going to do a poll for this one as well. So think about your answer. Think about your answer while I set up the poll. In which state of matter do the particles spread out to fill the whole container? Solid, liquid, gas, or liquid and gas? Think about it and then have your say in the poll. Interesting. We're not quite at the 90s this time. We're quite split, actually. We're quite split. Have a go. Again, even if you're not completely sure, have a think about what you've heard so far this lesson. Think about the particle arrangement and make sure that you've read the question really carefully. Particles spread out to fill the whole container. I'll give you another moment while I draw some containers. Oopsie daisy, while I draw some containers. No spoilers. Thank you. I agree. Okay. I'm going to end the poll in 5, 4, 3, 2, 1. Ooh, interesting. Now, 50% of you have said C, gas. And then the next was B, liquid, and then the next was liquid and gas. Oh, go on, Lara. If you want to give a clue, absolutely, before I reveal the answer. But let's start with the, not many said solid, so I'm going to remove solid as an option. Oh, actually, that's not true. 14% of you said solid. Now, think about a solid. Let's take, again, like my phone, okay? If I put my phone in this box, is it going to spread out to now fill the whole container? No. Okay, it's going to keep its shape, it's going to keep its volume. Now, if I take a liquid, let's say water, and I put some water into this box, is it now going to spread out to take up the whole container? No, it's going to chill down there at the bottom, right? At the bottom of the container. But if I now put a gas in this box, is it going to spread out to fill the whole container? Is it? Yeah. Yeah, it will. So the answer is C, which was 50% for gas. I'm hoping that the other 50% have now understood and have moved on to that other 50%. Okay? Melvin, why no? Go on, talk to me. If you're not quite sure, then please do ask me a question. I love questions. I really, really do. Okay? As you're typing your questions, I'm going to go to the next one. Okay, good. You're with us. Wonderful. Next. Ooh, true or false? Particles in a solid cannot move. Should we do a poll? Particles in a solid cannot move. How do I feel about this question? Let's see. Oh, interesting. Which one has more kinetic energy? So gases, some fish will have the most kinetic energy because that's moving around. And solids will have the least kinetic energy. Ooh, I'm going to end the poll in 5, in 4, 3, 2, and 1. I think this is a bit of a trick question, right? Because if its particles cannot move around, then that's true. Particles in a solid, they can't move around, but what do particles in a solid do? What do they do? They, thank you. They vibrate in fixed positions. So for that one, I'm actually going to say that this is like that. Okay. I feel like depending on how you define move, you could say either. As long as we understand they're not moving around, but they've still got some movement energy. Okay. Are we on our last question? Let's do this last question. Okay. Which of the following is not a characteristic of gases? This one, I'll just take your answers in the chat. Not a characteristic of gases. Not a characteristic of gases. A, B, C, or D. A, fixed volume. B, takes the shape of the container. C, move freely. D, particles are far apart. I'm seeing lots and lots of A's, and I would have to agree. For fixed volume, that is definitely not a characteristic of a gas because gases can spread out and take up more space. Yay. Okay, do we want to do this? Let's do this last one because we're here. We spoke about this earlier, but let's put it into writing. Lovely, Lara. Explain why gases can be compressed, but solids cannot. Even put some keywords down at the bottom to help you out. Why can gases be compressed, but solids cannot? I'll start off the sentence while you have a think about the end of it. Gases. Ooh, Shiv, I agree, but which one are you talking about? Which one are you talking about? Let's be as specific as we can. Gases can be compressed. Have space between what? Space between them? What do we mean by them? Who's them? Thank you. There is space between the particles. Lovely, lovely, lovely. Oh, Lara, that's a great question. I think let's talk about that in a moment. Okay, whereas or however, there is no space or little space between particles in a solid. Now, Lara made a really good, raised a really good question, which is about sponges. right? Now, if we think about a sponge, let me draw a sponge. And I apologize in advance because, like I said, my artistic skills, that's not my strong suit, but I try because, why not? We're here, might as well. No judgment zone. Right. This is my sponge. Now, a sponge is a solid, but when we're squashing a sponge, what are we actually squashing? Are we squashing the solid or are we squashing something else? What do sponges have in them? There's lots of something in sponges. What are these little circles? I know this looks like cheese, but what are these little weird circles that I've drawn? Oh, lovely snipe bite. Thank you, Yashi. There's lots of spaces. There's lots of air pockets. And air, we know, is a gas, right? There's lots of air pockets in a sponge, and air is a gas. So when we're squashing a sponge, what are we actually squashing? Are we squashing the solid? Not really. We're squashing the pockets of air that have got lots of space between them. Okay. Great question. Thank you for asking it. Okay. Okay. Really well done. Now, wonderful. I'm so glad that you joined me this afternoon. But before you go, if you have enjoyed this lesson,